Given the 6 instructions, now let's see how we can use FPGA to implement the same functionality but with improved performance and resource utilization. The idea is to unroll the CPU hardware. Specifically, we want to use the FPGA resource to come up with a design that implements the exact function that this kernel function needs. The idea is to look at the resources that are not used in every step of this execution. First, the instructions are fixed, so let's remove the instruction fetch unit since we don't really need to fetch these instructions. Second, there are certain ALU operations that are not used in each of these individual steps, so we'll remove those unused ALU operations. As a result, for the load instructions, we'll have the load unit along with the ALU path and the writing to the register file. For loading the constant, we don't even need the load unit. We just pass in the constant value to this register and then feed the value to the register file. For the multiplication operation, we'll keep the register file and then the multiplier, and then also this path to feed the result back to the register file. Similarly, for the addition operation, we'll keep the ALU, the adder for the ALU operation. For the store, we'll use the store unit along with the output from the register file. The next thing we see here is the load and store units are not used all the time. So remove the load store units that are not used during this execution. And the next step is to wire up the proper values. We can form the proper dependency graphs. Specifically, we'll use the value load from address 100 for addition operation. We'll use the value load from address 101 for the multiplication operation. The constant value will be stored here to supply the operand of the multiplication. And we'll pass along these values through these wires. Likewise, the result from the multiplication will be sent to the store unit to store back to the memory. In this way, we can propagate all the states and the values. Finally, we realize that some of the operations, for example, the load operations, because we're loading 2 memory operands, and since now we have multiple load units, then we can reschedule these load operations so they can be done at the same time in order to improve the performance. We'll remove the data and units that we don't use because we can instantiate multiple load units, so there's a chance that we can perform these 2 load operations at the same time in order to improve the performance. That's exactly what we're going to do. We'll reschedule these operations to leverage the abundant resources on FPGA. As a result, we can perform the same operation, achieve the same result using specialized dedicated resources. So what we just did was to customize the data path on the FPGA to match the exact algorithm. Remember, the high-level code is to perform this multiplication on the constant number and memory operand and accumulate the product with the other memory operand. To implement this function, we build a customer data path where we have 2 load units which can load both memory operand at the same time. We also initialize the constant value as the value in the design. Then we perform the multiplication operation, then we feed the product into this adder. the result from the addition will be then stored back to memory using this store unit. So we built the design by choosing exactly what we need: the operations, the data width, the memory size, and the configuration. In such a way, we can improve the throughput of the design, reduce latency, and improve power consumption. Look at this kernel function again. This kernel function performs element-wise addition on two vectors. And to illustrate this operation, we have two vectors, each has 8 elements, A and B, and the kernel is going to perform element-wise addition on these two vectors and put the result into answer C. We know that we can design a customized data path to implement the exact function that this kernel requires. That is to load the two memory operands from memory, perform the addition, and store the result back to the memory. And to perform this operation, we can launch 8 work items for the vector add. And we give these work items IDs from 0 to 1 to 2 up to 7. Because we have this customized data path, we can leverage the registers between these stages and use them to form an efficient pipeline. So in the first cycle, we can have the first work item supply the addresses to the two load units to load data from the memory. As the load units works, as we proceed, the two load units will load data and have the data ready to these two registers. At the same time, we can in fact supply the address from the first element from the work item 1 to these two load units. The goal is to get them ready for loading to prepare data for the work item 1. As we move on to the next cycle, the data that have been supplied to the adder will perform addition on the data for the work item 0. So at this cycle, the sum of these two numbers for work item 0 will be ready. At the same time, the data for work item 1 will be loaded from memory. And in the exact same cycle, the addresses of work item 2 for loading the data will be supplied to the two load units. So on each cycle, the portions of the data path are processing different threads. In the next cycle, the store unit will store the result from the adder and store that result to the memory location for work item 0. During the same cycle, the adders is performing addition for work item 1, and the load units have retrieved data from memory for work item 2. And for work item 3, it gets the memory address for these two load units for the loading operation in the next cycle. So in such a way, each cycle, the portions of the data path are processing different threads. So all these units are never idle. They are all being active, although they are working on different work items.